Good evening, everyone, or the people from Asian countries. And good afternoon to our speaker, Dr. Obedi Alves Santos, and other colleagues from Europe. And good morning to people from US and South American countries. We have Professor Antonio Azevedo also on board. Really happy to welcome him and welcome all of you. So it's really very nice to have Dr. Obedi Santos on board. He's an expert in spintronics. So I thank him first of all on behalf of my team, the Raj, Puspendra, Ajay, Sakti, and others, for accepting our invitation and joining this webinar series. So you are going to give now the 85th webinar. It's almost more than 21 months. And in few months, hopefully we'll cross the 100th seminar. And I really like to thank speakers like you who have been very kind accepting our invitation and joining this series. And also I like to thank all the participants who have been very supportive and very cooperative throughout this journey. So I like to now give a very brief introduction about Dr. Obedi Alves Santos, who is an experimental physicist originally from Brazil. He received his MS and PhD degree from University of Pernambuco in 2014 and 2018, supervised by Professor Antonio Azevedo, who is also attending the lecture right now with us. And Obedi also worked together with Professor Sergio Rezende. During the PhD, he primarily worked with ferromagnetic resonance, spin bumping effect, spin seebeck effect in a wide range of materials. In 2018, he started a postdoc at the University of Bigoza, where he collaborated with many institutes in Brazil and worked on spintronics. Since 2019, he's a postdoctoral researcher at the Janneke Institute for Advanced Material in the group of Professor Bart van Wees, where he is working, this institute at the University of Groningen in Netherlands. And his current research is focused on spintronic devices and magnonics, mainly on non-local magnon transport geometry. So we are really happy to have a very young emerging researcher in spintronics. And I'm really delighted to have you all. I just like to mention that during the lecture, we don't take any questions. If you have any questions, you can kindly write that in the chat box in case you want me to read it. Or you can just raise hands and we can take it during the question answer session. Also, I like to say that at the end of the lecture, before we take the questions, we will have a very quick photo session. So please turn on your camera for 30 seconds. When I say, and that time we will take a picture, and after that we'll have the question answer session. So with this, now the floor is all yours, Obedi, and looking forward to a lecture. Thank you so much.
Thank you. I think I'm really glad for the invitation. I hope that I can have a nice talk today. So I think maybe I can confirm that I can share my screen. And
yes, we see you.
So.
Yes.
Right. Okay.
It's all good.
Okay. So thanks once again, and I hope that that we have a nice evening. Well, I think it's evening there. I think it's still afternoon here, and maybe it's still morning in Brazil. But okay, let's go for it. So this is the talk, the main topics of my talk. So I'll discuss briefly about non-local magnon transport and devices, and also going to want to discuss a few challenges that may exist in this area, in this subject. So first, as a summary, what I'm going to talk about, I'm going to have a very brief introductions, discuss a little bit of magnons and how can you electrically and thermally excited magnons, you have magnon excitations. Then I move for devices and discuss a little bit or a few devices that we working on. three-terminal magnon devices, magnetic gauge effect, and how the anomalous spin Hall effect can contribute to the magnon conductivity, and then discuss a little bit of some challenging, some new results that we have, and also maybe some new future kind of devices, as I mentioned here, a diode. But okay, so as introduction, I have to talk about Magnus. So Magnus is the quantum excitation of the spin waves. So let's say that you have a magnetic material in the presence of an external magnetic field. So the ground state of the magnetization will be every spins of the magnet aligned with the external field. So you may think, okay, but which is the first excited state? So you may think that could be flip one of those spins, but in fact, this expend a lot of energy, and is more easy, or let's say more energy better. You, instead of flip one spins, spread out these deviations of spins along the lattice. So now you have what we call a spin wave. So instead of flipping one spins, you just take the amount of this angular momentum and spread out over the lattice. You have a low energy state, and this is the let's say one of the first excited states of the magnetization. So this is a spin wave, and of course, together with the spin wave, you have a wavelength and also a wave number or wave vector in this case. So the two main contributions of the Magnus, or let's say this energy that involves the spin waves, are before that, I have to mention that we are going to discuss a little bit more about Magnus on YIG. I think this is the main topic, one of the main topics of my talk, because Magnus can travel long distance on YIG, and I hope that at the end of this talk you may also think or understand that the magnonic devices also can be implemented in the near future or future electronics. So this is the basically of Magnus and spin waves, and one of my goals of my talk is I hope that at the end you fully understand that sketch. So this is a artistic, let's say, impression of a no-local Magnum transport. So you have one strip, another strip, and the Magnus traveling through it, through some material. I hope that at the end you just look at to this picture and you visualize all the things that are explained in this talk. But before that, the main focus of this talk is on YIG. YIG is a ferromagnetic insulator. Ferrimagnetic means, of course, that you have antiferromagnetic coupling, but with different magnitudes of magnetization. So effectively, you have a ferromagnetic material. It has a very low damping parameter. So that means that the acoustic and magnetic losses of the YIG is quite small. Another thing that's really important, and that is that for our case, is that the magnon relaxation length of the YIG is quite large. So it means that a magnon can survive for a long distance, and this will be very important for us. But okay, so let's say I have magnon here, a different wavelength with different wavelength of magnons correspond different magnons. And the question is, okay, how can I distribute, or how can I explain, let's say, those magnons as function of the wavelength? So you can look at this, take a look for the magnon dispersion relationship. So this is more or less the magnon dispersion relationship. The two energy that's involved in the magnons are the exchange energy, which is proportional to kg squared, So it, of course, is the energy between the exchange direction of the first spin with the first neighbor, and the dipolar energy. So the dipolar energy, it's an energy with large action. So it corresponds of or let's say we'll see that that is more important for very large wavelength. Besides very short wavelength, high frequency, high energy are what the magnons that are important to this is the exchange magnons. So this is more or less there is a few before that there is a few branches of magnons. As you can see here, I have magnons with K perpendicular to the magnetization, K with parallel to the magnetization, or let's say if the magnetization it's pointing out of plane of your YIG film. Because in our case, your experiments, we always have the magnetization, or let's say the external magnetic field on the plane of the film. So we may focus on the surface mode and backwards volume mode. So and everything that is between the backwards mode, this one, and surface mode, this one, you can understand as a magnet. So again, I think this is also it's showing here different wavelength or wave vector for and the energy that correspond to these ones. And as you can see here, this like a dip here is correspond to the dipolar energy that are important. So the dipolar energy are important for wave very low wavelength and the low energy, low frequencies. For the magnons, because the energy of exchange energy of magnons is proportional to K square, for very high frequencies, very in the range of terahertz, these two branches becomes basically one. It's not drawn here, but it basically becomes one branch only. And I think this will be important in the one of the latest slides that I will show. So before enter in the discussion of non-local geometry itself, it is important to mention that most of our experiments is based on the spin-Hall effect, which is, well, by itself, I could spend like a half hour just talk about the spin-Hall effect. But in our case, we're gonna use the spin-Hall effect for the experiments that we're going to do. So we have the spin-Hall effect, which can be understood as a conversion of charge current into a spin current. So let's say that I have a charge current here with spins ups and down, passing through some material with a high spin orbital momentum, spin orbital coupling. So in this case, I have opposite spins moving to the opposite directions. So I create a spin accumulation here that is the opposite of this spin accumulation. Because I have one electron moving up and one electron moving down, I do not have a charge current across in that direction, but I have a spin current in that direction. So basically, what is the spin in the spin-Hall effect, I have a charge current becoming a spin current. So which means that, let's say that I have a strip of platinum or high stock material as a palladium, tantalum, tungsten. I send the current. This current creates a spin accumulation opposite directions from the bottom interface to the top interface. And as you can see, this you can understand this as a spin accumulation. So this is more or less how the spin accumulation is distributed along the Z direction here on the platinum strip. And of course, because of the Onsager reciprocity, the inverse effect also can exist. So if I inject a current, I create a spin current, a charge current, I create a spin current. The opposite is also true. If I create a spin current, let's say across the Z direction on my platinum strip, this can build up, this will be build up a voltage on the edge of that strip. I think it will be more clear in the few next slides. But this is the main effect. This will be important for us for the no-local experiments. Okay, so let's say that I have now a strip of platinum deposited on top of the YIG film, and I send a current here. So in the moment that I send a current here, I create a spin accumulation at the interface between platinum and YIG. This spin accumulation can have two effects. First, if my magnetization is perpendicular to the spin accumulation, the polarization of my spin accumulation, I create a torque in my magnetization. And this, well, basically my magnetization would try to move towards my spin accumulation. However, in the other case that my spin accumulation is parallel to my magnetization, I do not have a torque, but I can create a magnet. So now this is the one way to visualize that. So I have a spin electron, free electron with spin down here, enter at the interface. So in that moment, this spin of this electron, it will interact with the magnetization of the YIG, and this will create a magnon. So after this interaction, my spin will flip direction, which means that every spins that came at the interface caused by the inverse spin Hall, caused by the spin Hall effect, will create a magnon. And here it's important to emphasize that the interaction here that is predominant from the electron of the spin with the magnetization of the YIG is majority caused by the exchange. So that means that I have an exchange interaction between my electron of the platinum and the magnetization of the YIG. And this will be important to understand in which range of magnons we are talking about in the no-local experiments. So this is what happened on the first strip. But if I have a second strip further in my YIG film, the opposite effect can happen, because now in this strip I create a magnon. This magnon will travel long distance, as I mentioned before, that magnons can travel long distance on the YIG. This magnon will travel on the YIG, and this magnon can interact with the platinum strip in the opposite way. So now I have a magnon coming into the interface of platinum and flipping one of spins of the electron, but again with the exchange interaction. So this will create a spin accumulation. So we'll build up a spin accumulation on the detector. And once again, because of the inverse spin Hall effect, now I build up a voltage across here. So this is in fact, is a very, very nice thing, because I inject a current here, create a magnon, because YIG is isolated this way. I don't have leaking of current. The current will be on the platinum strip, create a magnon. This magnon will travel through the YIG film, reach the platinum, and the opposite effect will happen, and I build up a voltage. And this is a very nice thing. And as you can see in the few after a few slides, that we also can play around with the magnons that are in between. We could, let's say, increase the number, decrease the number, or I don't know, maybe block. But okay, this is the basic. So let's go for a little bit for more visualize, or let's say how real this guy that thing are. So for example, I can show here the steps that we made for the fabrication of the samples. So I have I take a YIG film. On top of the YIG film, I design by lithography strips of platinum with different distances. which I apply current one way on strip, detect a voltage in the other one. So usually we deposit 80 nanometer thick platinum strip on this YIG. Then I design the leads and the pads that afterwards make a wire bond, connect to my setup, and make the measurements. So of course, the whole process happens on the clean room. As you can see, sometimes we have some problems. As you can see, I don't know if you can see it, but there is a gap here. Maybe a dust, I don't know. Sometimes not works, but okay. So the next step that I'm just summarizing again, the other way to visualize this, I have the injector, apply a current, create a spin accumulation here. This spin accumulation diffuses, create magnons that diffuses along the YIG. On the detector, will have the opposite effect. But one characteristic that's very important of the interaction of platinum and YIG is because the interface of platinum and YIG is quite transparent for Magnus. That means that I can create the majority of the spin accumulation that I create at the interface. It's delivery to the YIG creating Magnus. The opposite effect also happens, so that my detector can absorb Magnus. So which means that the platinum strip is a good spin source, and it also is a good spin drain. As you can see, I hope that there is this dark region here across the detector. This happens because my detector is absorbing Magnus and create this dark region. So here I have more Magnus, here I have a short Magnus because my Magnus are absorbing and create a voltage. Once again, I have a spin accumulation. The spin accumulation creates a projection along the magnetization. The magnetization projects spin accumulation on my detector, and because of this, I have a cosine dependency as function of the angle on the injector and on the detector. This creates my cosine square behavior. So, but at the same time that I apply a current and create a magnon by electrically, I also have the thermal effect because I heat up my sample, and because now I heat up my sample, I now create a thermal gradient across my devices, and because of this, the spin-Seebeck effect can happen. I do not emphasize here, but the spin-Seebeck effect creates a spin current at the same direction of the thermal gradient. So in this case, I also gonna have a spin accumulation that creates a magnon accumulation, but is not anymore dependent of my injector. So therefore, just have a cosine dependent. So these measurements that we made it, we apply AC current. Because of this, we can detect the electrically injection of magnon at the first harmonic, and we detected the thermally magnons at the second harmonic. So once again, I have now a cosine of angle, and if I measure as function of magnetic field, I just observe a step because this is simply my magnetization flipping from one direction to other direction. So, okay, let's move a little bit for devices. So what can do it with these no-local experiments? So one thing that I want to discuss is that we can put a third strip that can be permalloy or platinum. The first experiment that was made on this kind of geometry was using platinum. And what happens? Well, if let's say that I have apply a AC current here on that strip, I create magnons that will travel through the YIG and reach this other platinum strip. If now I apply a DC current on the middle strip, I will create more magnons in the channel, or I can annihilate magnons in the channel. So this is the idea of the Magnum Transistor, that I apply AC current here, detect AC voltage here, and depending of my current, DC current that apply in the middle one, I can increase the numbers of magnons or decrease the number of magnons. So basically what I'm doing is increasing or decreasing my magnum conductance. So this is more or less how can we wrote the magnum conductance, the magnum conductivity, sorry, conductance or magnum conductivity in this case. So my magnum conductivity will be independent of the current, of course, but it will depend of the current that apply and then which direction of my projection of the spin accumulation of the middle strip and my direction of my magnetization of the YIG. So what at the end, what this happened, this created a new angular dependence of my voltage. So here, if I go back a little bit, here I see a sine square, but because now I can apply a current and create more magnons in between, I have a cosine square plus a cosine third term. Because now, if my spin accumulation have the same direction of my magnetization, I create more magnons. So as you can see here, I hope that you can see it, but that is the yellow curve here. Yellow dots are experimental data. The angular dependence, as you can see, and then 0 degrees and 9 degrees are basically the same. But if I apply a current, let's say a positive current here, I annihilate magnons at 0 degrees, and I create more magnons at 108 and minus 180 degrees. So this, I create this unbalance, so I can control the numbers of magnons that reach the detector by this third strip. So as you can see here, so this component are completely linear with my current that as described here. But okay, let's say that now, instead of using platinum, I use my permalloy strip. So instead of I put a platinum, I use permalloy. So what will happen, and what we find out is that the magnons will be absorbed by the permalloy, even if I do not apply any kind of current on my permalloy strip. So I have my platinum strip here, creating magnons. This magnon will travel through the YIG underneath my gate of permalloy, and then being picked up by the detector. However, if the magnetization of permalloy are in 90 degrees with the magnetization of the YIG, the permalloy will be absorbed magnons. But the other way around will not happen if my magnetization of permalloy are parallel to the YIG. So it means that I create a kind of a gating effect, just rotating the magnetization of my permalloy. And why this happened? Well, this happened because we are talking about the strip of permalloy. So this strip, because now permalloy is a magnetic material, this strip has a very, very, very hard shape anisotropy, which means that that at low field, my permalloy are aligned with the external field, but at high field, my permalloy is aligned with the external field, but at low field, the permalloy stands, the magnetization of permalloy stands along the strip, the direction of my strip, which means that for, as you can see here, for low field, I have my permalloy at 9 degrees, but at high field, my permalloy is parallel to the permalloy, the magnetization of the YIG. So that means high Magnus traveling through the injector detector, low Magnus traveling through the injector and detector. And this is more or less what you can see here. So I have what we call no local Magnum resistance, which is simply the voltage on the detector divided by the current on the injector. So as you can see, this my no local voltage or my no local resistance increases as a function of low magnetic field. And this corresponds to the rotation of my permalloy magnetization. So this is what we call the magnetic gating effect. But on top of this, because permalloy also have the possibility to convert spin charge current into a spin current, which means that my permalloy can also create Magnus as the same way that platinum does. That means that I also can modulate this Magnus by applying a current on the middle, in the middle strip. But because, and this I think becomes a little bit more complicated, because the behavior of the component of the spin to charge component of the YIG of the permalloy becomes way more, I mean, complex as you can see, because before I just have my Magnum conductivity that's proportional to the current and the angle, but now I have another component, and as you can see, it gets a little bit more complicated. And because I have a lot of cosines, sine squares, and so on and so forth, and one can say, of course, you can fit everything with this. You can also fit an elephant with this, but well, we don't need to do it because someone already does this, and as you can see, you can draw an elephant on top of this. But so, which means that we have to downgrade. We have to go for some condition that is way more simple. So let's say that for low field, in the case of low field, my permalloy magnetization will be aligned along the strip. So in this case, I will have that theta equal to 9 degrees. So my equation of no local, so my first harmonic, second harmonic equation of no local will become now very simple, as the same as before, cosine square plus a component of cosine a third. And the second harmonic, at high field, I also have a very quite simple equation. So now I have a component proportional to the cosine square and another component proportional to cosine a third. So it means that I apply low magnetic field, make my angular dependence, and fit with this equation that I showed before here for low field and high field. And when I do this, I see a dependence of the anomalous spin Hall effect, because now my permalloy can convert convert charge current into a spin current by the spin Hall effect, but he also can convert by the anomalous spin Hall effect, which is magnetically dependent spin to charge conversion. So I can analyze this data. I can see that at low field, my efficiency of modulation is lower than at high fields, and this can it was explained by the contribution of the anomalous spin Hall effect. So this is what we showed in this paper. But the other thing, and here I hope that we not have time enough to discuss the second harmonic, because this was the results that I see enhanced of modulation that's happened because of the anomalous spin-Hall effect contribution. But for the second harmonic results, well, the things get slightly complicated, and we cannot fully explain it, because at low field, instead of my modulation efficiency decreases, in fact, it increases. And this is still an open question, why this happened. And I think we can go more in details in the paper. But let's talk about a little bit of challenges. So let's see what's new things that can come out from this kind of geometry, this subject, this kind of experiments. So let's say first, it's possible to make that we could have a Magnum diode, let's say, for example, and understand the magnetic diode as apply current here, AC current here, detect a voltage there, and somehow I create a barrier in the middle of my YIG. So how can we do it? Well, so far we just have a theoretical paper about this. This paper was published in the beginning of this year, and what it suggests is that let's say instead of ferromagnetic material as permalloy that I used before, if you have a superconductor material, you could create this kind of barrier. The other thing is that this kind of barrier do not happen, let's say, in the case that I have a very high Magnum modulation, because if I go back a little bit here, I can be easy to see that that my modulation not changes a lot. I mean, if I create a Magnum, I increase the magnons that flow between injector detector, and if I destroy a Magnus, of course decreases, but I cannot reach a complete minimum. I cannot like completely block this the Magnum conductivity or the Magnum flow between injector detector. Even if I use in this paper use a very thin YIG film, I could not reach this. I reach a minimum, but not a block. So it's still an open question if indeed we can do it kind of Magnum diode or some kind of device like this. The other challenge that we have so far is that what is the thickness dependence of this non-local Magnum transport. So let's say that I have a very thick YIG film, 1.5 micrometers. So I have injection, distribution of magnons, and the detector. So if I decrease the YIG film, I think it will be more easily to see that I decrease the material that transport magnons. So at first sight, you may say that you should expect a decreasing in the non-local Magnum transport. So my voltage that I measure here will be diminished because I have less material to transport magnons. But in fact, what we observed experimentally is the opposite. I think maybe it's not so easy to understand from this figure, but the next one will be quite easy to understand. But this is the angular dependency for, let's say, 3.7 nanometer YIG film, 5.9 nanometers YIG film, 200 YIG film. So this line here is 200 nanometers YIG film, which reach around 150 ohms per meter, which means voltage divided by the current. But you can see at 7.9 nanometers, so very thin YIG film, I have around almost 700 ohms per meter. So why this happened? And this is one thing that we are exploring now. So I think here is more easy. For the same distance between injector and detector, if I decrease the thickness of YIG, I see that my non-local resistance, or is be easy, the voltage divided by current, increases as function of the thickness. So was quite surprising, because once again, if I have less material that transport Magnus, I should expect less Magnus that reach my detector, but not seems like this. And this is a very good experiment, very interesting founds that we observed, and we are currently working on to explain this. So one way to let's say to write this non-local resistance is using this equation that basically your non-local resistance, your voltage, are proportional to the Magnum conductivity, proportional to the thickness of YIG, proportional to how efficient are your material to convert spin to charge into magnons, and of course in injector and detector, and also the distance that we have between injector and detector. So the previous paper that, or let's say the previous paper that work on this and try to obtain a magnon conductivity from the YIG, they observed that the YIG, let's say with a thickness of 200 nanometer, has a magnon conductivity of 5 to the power of 4 Siemens per meter. So this is, I mean, was the number that they found out. But what we found is that for YIG thickness of 3.7, 5.9, 7.9, the magnon conductivity can reach 1 to the power of 8. So it's quite surprising why we have so high magnon conductivity for very thin YIG films. I think this is the paper that we are trying to explain this effect. We show the experimental data and try to explain those results. So, but how can we confirm this data? So this data, this number, I can obtain it using this equation from the experimental data that I have. But how can I confirm? One way to confirm this, we use the finite element modeling for this. So I have the equation that describes how magnon can flow on the YIG. I use the console mode physics to simulate that. So this is where we make this graphics. We made it on console mode physics. So we now can, let's say, I get the experimental data, so I have a few distance between injector and detector. So each data, it's important to emphasize here, each point here is an angular dependent measurement, right, for a fixed distance between injector and detector. So as you can see, we have done a lot of measurements. So each point is one separate device in one YIG, one thickness of the YIG, and with this we can see how the local measurements on a local voltage decreases over distance. And now I can use my finite element modeling to see which kind of or let's say which is the value of the magnon conductivity that can fit my experimental data. So I make this for every thickness that we use in our experiments. And with this, I can draw the magnon conductivity over the thickness. So as you can see, we have the experimental data. This is the experimental data. So a flat, then increasing. And the magnon conductivity that I can obtain from that. And I see also increases around 1 micrometer. But this is not counterintuitive. Yes, a little bit, but we try to explain in our paper. So as you can see, the other thing that's quite important is because we are almost reaching the lattice constant of the YIG. So which means that below these two lines, we are not talking about anymore about YIG, because YIG is a very complex cell with of the atoms distribution on this cell. The constant lattice is 1.2 nanometers. So we are almost reaching the unit, let's say a few unit cells of YIG. So we are mostly limiting of 2D YIG film. So this is not contradictive, yes, a little bit. And in order to explain this, we have to take into account all the modes, all exchange modes of the magnons. And I think, well, I think I don't have too much time, but one way. But the question is how much space or how much magnons I have under for, let's say, for different YIG thickness. And this is, I think we can oops, yeah, I think we can obtain this for with this graph. So you can calculate the numbers of occupied modes on the every YIG thickness. So this is what we get. You can see a straight line by log graph. But one way, or let's say more easy way to understand this or show this is that if we take the frequency of each mode. So I have now this distribution for n equal to 0 to 1, 2, 3, 4, 4, up to 10 mode of the magnum, of my magnum excitation. So as you can see, for thickness around, let's say, less than 10 nanometers, I only have a few modes or available, or let's say a few modes of Magnus available into the system, which means that this increasement of non-local resistance, and of course, increasement of my Magnum conductivity, is directly related of how is the number of Magnus available in the system. If I have low subbands of Magnus available, I could have more. I have more concentrated, or let's say coherent excitation of Magnus. So I have way more or less losses between the exchange between the bands, and my Magnum will travel and longer, and I increase my Magnum conductivity. So this is more or less what we are trying to aim to explain this data. Please take a little bit look further in our paper that we have a little bit more discussion about this. And I think, well, I have reached most the end of my talk. And again, I go back to my first artistic expression, illustration that I showed you before. And well, that's basically summarized everything, right? I have my current here, apply a current here. This current creates a Magnus that travel through my material, reach the detector, and I pick up a voltage. So this is more or less what we have done. And we try to understand better how the Magnus travel and how can I excite more Magnus into the system. How can I increase the efficiency of Magnum transport, and how can I control also? Because as you can see, as showed before, I also could modulate these Magnus by putting a third manuscript or third strip or these other devices, right? So I think with this, I have to thank all the co-authors, and then, well, thank you for listening.
Yeah, hello, Obed. Very nice talk. Thank you so much. And on behalf of everyone, I'd like to for an excellent talk. Before we go to the question answer session, I like to now request you to stop sharing for a second. And I like to
sure.
request all of you to switch on your camera. So I see Antonio has already switched it on. Yeah, hi. So others I request, and then we can take a picture. All right, a lot of other people have not switched on. Okay, so I'm taking a picture now. Smile. All right, so you can switch off your video, and Obed, you may kindly share your screen.
Oh, sure.
And yeah, if you have questions, please raise your hand, or in case you want me to read your question, then write your question. So maybe I can begin with some very simple questions. In the beginning, when you saw this Pormalo strip, I wonder if the Pormalo strip has any anisotropy, or the question is, does this anisotropy play any role when you want to, play around with the Pormalo?
Yes. Yeah, I think. Well, in the middle part of my talk, I needed to speed up, otherwise I'll not reach the time. So sorry about this, but yes, definitely, this is what the main goal of the paper that I published last year in the group. That if you have like the Magnum Transistor using platinum, because platinum is not a magnetic material. Well, it's not any kind of magnon dependence, or let's say external magnetic dependence of how the spin accumulation are created in the middle strip. But when I use permalloy, yes, I have this. I have two components, to be honest. I have my current can create spins which is independent of my magnetization of the permalloy, so what we call spin Hall effect of permalloy, right? And I have another component that is dependent of the magnetization of the permalloy, which means that if my permalloy is let's say pointed, depending on where my magnetization of the permalloy is pointed, I can create more or less spin accumulation. So the question that you made is really important, and I think I can go back here. Let's say in this case that I have a strip of platinum or a strip of permalloy here. Because of the shape that I have 8 nanometers in the case of permalloy. Is 12 nanometer thick permalloy. With this shape, the magnetization of the permalloy would be aligned, or let's say tend to be aligned on the strip. So that's why I think I draw this kind of behavior. If my magnetic field, which it's pointed to in y direction, are in low value, so because of the shape anisotropy, my magnetization of permalloy will be aligned along the strip. So I needed a high magnetic field switch, and this was of the reason, or let's say why the magnetic gate effect could be observed, right? So the answer, yes, the shape anisotropy of the permalloy is really important in this case, and because of this, we could separate. Well, let's say first we could measure, observe the magnetic gate effect. We could address the spin Hall component from the anomalous spin Hall component in the Magnum Transistor.
Okay, thank you so much. Yeah. Are there other people having some questions? Please raise hand. While they're doing, maybe I can ask one more question. So when you explain the spin-Seebeck effect, I was not very clear. Did you make intentionally a temperature gradient, or it was just automatic?
Sorry, I create what?
The temperature gradient.
No, I mean, I did not define the thermal gradient because I'm sending a current to excite Magnus, right? To transport Magnus over the YIG. I also heat up my sample. So which means that that together with this heat up, I have a great thermal gradient over my YIG film, and then I have different points with different spin accumulations. So this is how, let's say, I can pick up by the second harmonic my spin accumulation that comes from the spin Seebeck effect. Indeed, I have to say that I should explain a little bit more the spin Seebeck effect. I could not have time to explain the spin Seebeck effect, but yes, the spin Seebeck effect is create this thermal gradient over my sample that I can pick up by the second harmonic. So it's not the electric excitation of Magnus, but the thermal excitation of Magnus.
So you are telling that the thermal gradient actually was created due to the Joule heating, yeah?
Yes, exactly.
Okay, that's clear. Okay, there is a question, I think, by Puspendra. You want to ask or you want me to read?
I can ask.
Okay, please.
So you in last part of talk, you have told you have shown the number of magnons in YIG films. So with the increase in thickness, number of magnonic modes are increasing. You have showed it in last part of your talk.
Yeah.
So how one can decide that how much magnon mode exists in the film, in the ferromagnet? And yes, the first part of my question is this one. And second, if even we can control the number of magnons, how it is going to help in application point of view?
Okay, that's a good question indeed. Well, so the first part of the question, how much, what is the, let's say, the maximum of Magnus that I can create in the system, right, between injector and detector? Well, this is a very good question. I do not have here on extra, but there is a paper that that's also show this kind of behavior, and basically what they say is that you could have like kind of threshold, maximum threshold, where of the amount of Magnus that you can create it, which is when, let's say, when you reach some kind of zero damping. So let's say that the current that applied, I create a spin accumulation. This spin accumulation inject the Magnus, but also could change the damping of the YIG. So which means that the maximum value that I could have is when the current, the spin accumulation, let's say reach the let's say, how can I say, reach all the dampings of the YIG film. So this would be like the maximum. I don't have here, but maybe I can send it afterwards by the link, the link of this paper that I'm just talking about. The second part is well, how this can be used for application. Well, a lot, because we are one of the main results that I was going to show it today is the Magnum Transistor, but the efficiency of the Magnum Transistor is still quite low. And I mean, the efficiency of the Magnum Transport is still quite low. I know that I can apply current, create Magnus, and be detecting the second strip, but this efficiency is still lower. So learning, or studying how can I increase the efficiency, or how can I increase the numbers of Magnus, are indeed very important for future application, or let's say application point of view, right? I hope that still be clear, but yeah, this is more or less how I could answer this.
Okay, so I have one more question
Yeah.
regarding anomalous spin Hall effect. So this is happening in ferromagnets. So how in few people have shown that in anomalous spin Hall effect, the current generated spin current direction is bothward, upward as well as downward, means towards the top non-magnetic layer as well as towards the down magnetic layer. So, but how this is happening? So, I'm not very clear about this. So, can you explain that part?
Okay, yeah, I think I can. Well, the nature of the spin Hall effect is the interaction of the spin of the electron with the angular with the let's say the impurities on the platinum with high SOC, right? With spin orbital momentum of the platinum, for instance. So of course, because in the platinum, this is caused by the impurities in the platinum. You do not have a magnetic, let's say, counterpart of the spin Hall effect. But in permalloy, because you have the magnetization of the permalloy, you have now some a kind of orbital interaction between your electron with the magnetization. So this creates a kind of the anomalous spin Hall effect, or the anomalous part, or let's say the magnetic dependent part of my spin accumulation. There is this whole discussion about if those two effects are basically the same or not. And I have to say that this is a very good point of view, very good question. And well, this is still on debate. There are some people that say that it's basically the same. The spin Hall effect, the anomalous spin Hall effect is basically the same. But I disagree, because of course the anomalous spin Hall effect is the spin Hall effect that depends of the magnetization. Because understand that the magnetization also interacts with the spin of the electron, and this creates a deflection that is dependent of the magnetization. So I think I hope that I could answer that. I think.
Yes, sir. Thank you, sir.
Okay, thank you, Prof. Sendra, and thank you, Obed. Any more questions from anyone? Kindly raise hands. Okay, seems not the case. So thank you, Obed. Maybe you can stop sharing. I like to present
Okay, sure.
a memento to you. All right. Very nice talk. I mean, I really enjoyed. Do you see my screen?
Yeah.
Okay, so on behalf of the W2S team, it's my great pleasure to present you this digital plaque. I hope we can meet soon one day, either here or in Europe somewhere. And I would love to welcome you in our campus, which is very nice and beautiful. So I read it for you. So WPS Seminar Webinar Series on Spintronics, National Institute of Science, Education and Research, NICER, Bhubaneswar, India, takes pleasure in presenting this plaque to Dr. Obedi Alves Santos from the Jennicke Institute for Advanced Materials, University of Groningen in Netherlands, in recognition and appreciation for being a valuable speaker to give a lecture on non-local Magnum transport in YIG, devices and challenges. So thank you so much for your excellent talk.
Thank you.
We greatly appreciate your time and efforts. I hope to see you around. You are always welcome to attend any future webinars and also disseminate the information in your group. If anybody wants, it's just free. No obligation, so anybody can listen to it. So anyway, so thank you so much, and I look forward to you some other time, and hope to meet you soon in person somewhere. Okay. Nice. Thank you so much.
Okay.
Take care. Have a nice day.
Have a nice day.
Bye bye all.
Bye.
Thank you. See you next week.
See you.
Bye. Take care. Thank you.